Hello, and welcome to ME 397, the Product Design Laboratory for the online master's degree program in mechanical engineering at the University of Texas at Austin. I'm Dr. Rich Crawford, professor of mechanical engineering, and I'll be teaching this class this semester. So in this first segment, I want to introduce you to the class and give you an overview of what we'll be studying. First, a little bit about me. As I said, I'm a professor of mechanical engineering. I've been at the University of Texas at Austin since 1990. I got my bachelor's degree in mechanical engineering from LSU. Got my master's and PhD, both in mechanical engineering, from Purdue University. Throughout my career, I've taught a variety of design classes. I've taught a number of graduate design methodology and project-oriented classes. At the undergraduate level, for my first 12 years of my career, I taught an undergraduate design methodology class. Lately, I've been teaching a design projects class, or capstone class, in mechanical engineering. I also teach classes in geometric modeling and computer graphics at the graduate level. My research currently focuses on development of design methods, particularly for concept generation and for developing prototyping strategies. I've been involved in research in the area of additive manufacturing for 25 years. This is also known as 3D printing. I've been involved in it since before the time it became known as 3D printing. And mostly I focus on applications of those technologies as manufacturing processes. I've also, throughout my career, done a good bit of research in geometric modeling. So this chart is a depiction of the design process. It's taken from your textbook, authored by Otto and Wood. And if you look at any design textbook, you're going to find something like this, a graphical depiction of the design process. This is your author's version of it. They view the design process as occurring in three distinct stages: understanding the opportunity, developing a concept, and then implementing or embodying the concept. We're going to study methods that are applicable in each of these three phases this semester. Some of these have been highlighted on this chart. We'll start off with understanding the opportunity, and we'll focus there on understanding the customer needs, what it is customers are looking for in a product or a system that they would likely purchase. And we'll look at a number of techniques for understanding what those customer needs are. And I'll actually have you do some customer needs analysis with real customers as part of the project that you'll be working on in this class. What's not shown on this chart is an important stage that we'll also focus on, which is translation of those customer needs into quantitative engineering requirements, or what I like to call performance metrics. And performance metrics are aspects of a product or system that can be measured and that relate directly to customer needs, so that you can have a way to actually measure the degree of satisfaction of those customer needs. And we'll talk about a technique that is explicitly designed to help engineers translate customer needs into quantitative engineering requirements. Second box, developing a concept. We'll spend a good deal of time this semester on this phase of the design process, and we will focus on the techniques that are related to the highlighted aspects of concept development. The first is functional modeling, and I am a big believer in understanding what a product must do before you decide what it can be. And we'll see that functional modeling is a way to not only organize the design process, because it gives you a strategy to decompose a complex problem, but it also leads into concept generation, because the design process is open-ended. that means that there are multiple solutions to any design problem by definition. And so you can't just pick the answer. The best thing that you can do is generate lots of potential designs, potential concepts, and choose the best from among those. And functional modeling gives you a strategy for developing lots of concepts. If you can understand what the functions are, what the product or system has to do, there are typically multiple ways to accomplish a function. And so that's how it leads into concept generation and multiple concepts. We'll also spend a good deal of time this semester looking at concept generation techniques. I'll present a number of techniques from what we call our concept generation suite that we've developed here at the University of Texas. We will focus on some techniques that you've probably heard of and used, and others that you probably haven't heard of. Moving on then into the implementation of a concept, this is where you'll exercise the skills that you've learned as an engineer in terms of engineering analysis, and you'll apply that within the context of designing and, in our case, redesigning a product and trying to improve its performance. So we'll develop ways to actually model performance in terms of design variables and use those analytical techniques within that context. We'll also study how to physically model products or systems, and you'll have an opportunity to do that as well. So this slide gives a little bit more detail about that first phase of the design process as depicted by Otto and Wood. And it shows graphically what I was just speaking of, which is translating customer needs, which are depicted on the left in what's called an interpreted needs list, into a set of quantitative performance metrics or engineering requirements. And we'll use a technique called the house of quality, which is depicted on the right, to structure that translation process. And this is important because those performance metrics give us ways to compare different concepts and give us the criteria for choosing the best from among those concepts. This next slide is meant to depict the functional modeling techniques that we'll study this semester. And this particular technique, we'll study a number of techniques, but this particular technique is called a function structure. And it may look familiar to you. It looks like a flow diagram, perhaps, or if you're have a background in controls, it may look like a block diagram to you. And it really is a flow diagram, and it's based on abstracting a product or system as transforming a set of inputs into a set of outputs. So it's a very abstract way of thinking about what a product or a system does. And the function structure gives us a way to map those inputs through the transformations that occur inside the product or system that turn those inputs into the desired outputs. So we'll spend some time doing this. We'll do some of this together, actually. It's a very abstract technique, in my opinion. It takes some practice to learn how to do. We'll have some time. We'll have some opportunities to practice this technique at least a couple of times in your project this semester. This slide lists the concept generation techniques that I plan to present to you this semester. Probably everyone's heard of brainstorming, and we'll talk about brainstorming and the pros and cons of brainstorming, and we'll talk about a way maybe to use it where we can take advantage of its strengths and modify it and combine it with other techniques to overcome some of the weaknesses of brainstorming. The image on the top right over there depicts what's called a mind map, and that is a way to organize the results of a brainstorming session. The bottom right figure represents the results perhaps of a C-sketch session. C-sketch is a different kind of concept generation from techniques like brainstorming and mind mapping because the main mode of communication is graphical rather than the verbal communication in brainstorming and mind mapping. And so it gives us a very different way to think about putting or developing concepts, and it tends to help us think about all the functions, in particular support functions or secondary functions that a product or system has to do. And so we end up with typically more complete concepts using the C-sketch technique. We'll also talk about design by analogy. This is an area of current research in the design theory and methodology community, and it's an interesting approach to concept generation because many cognitive psychologists claim that most of what we think of as new ideas are actually analogies, where we take a solution from for a different problem and adapt it to make it work for a current problem that we're working on. And so I'll present some techniques to, I think one of the hardest things about design by analogy is actually identifying appropriate analogies. And this is an area of current research for me. And so we'll present some techniques that we've developed to enhance the ability of engineers to identify analogies for design problems. We'll also talk about this theory of inventive problem solving, or it's also known as TRIZ, which is a Russian acronym. It's a technique that was developed in Russia, and it's a unique concept generation method in that it focuses on breaking conflicts. And most design problems, especially mechanical design problems, are very coupled in terms of the relationships among design variables, and a lot of times, and performance metrics, and a lot of times performance metrics are in conflict with each other. And so TRIZ, or TIPS, is a technique that's focused on breaking through those conflicts. What we typically do as engineers is we'll compromise when we have a conflict. But what TRIZ does is attack the conflict and try to break through, and so that you eliminate the conflict. And the claim is that when you eliminate the conflict rather than compromise, you end up with more innovative solutions. This next slide depicts some of the steps in embodiment design. This, by the way, is a project that was completed in the undergraduate senior design class that I teach. Was the design of a long-lasting surveillance aircraft, MAV, a micro aerial vehicle. And you can see some of the steps that you might need to go through to develop that concept, to embody it. And so it shows different layouts, and that's typically what we do. We focus on different layouts or different geometric arrangements of the subsystems and components of the product, so that we transform the concept from its original layout into a more preferred layout. We also spend time trying to predict performance of the product or system, trying to optimize its performance in some way. So we predict how changes in the design variables will affect the performance of the product, so that we can pick the most appropriate values for those design variables. And that's what's depicted on those bottom two graphs down there. And sometimes we do that analytically. Sometimes we do that with physical experiments. And we'll talk about both approaches to that this semester. And what that should lead us to then is successful design. And these slides show the design that the students came up with for their surveillance vehicle. It's a Delta Wing gasoline-powered drone with deployable surveillance modules. The what's called the Sentinel ground sensor in the left-hand picture there. And these are prototypes that were built by the students. And so what we want to lead to is this is a good ending point for us this semester, where perhaps you'll prototype an improvement in a product that you're working on and demonstrate that it is an improvement and that it has better performance. So that's an overview of the class this semester. We'll get into more detail in the next segment. The next segment I'll talk about in more detail about this project that I'm going to have you work on this semester, where you'll apply those techniques and hopefully you'll have some fun doing it.